We can
Yeah.
hear you.
Okay, thank you so much. And thank you for confirming this. I want to welcome you to my lecture today. Of course, we are having a lecture today because of what I told us in class uh, previously. And we actually going to return to in-person teaching on Friday. Okay, so once again, I want to welcome you into this class. We started this material on Monday. We call this theory of convex function. Of course, the theory of convex, why do we find ourselves doing what we're doing right now? Um, we don't just do what we do. There's a reason why we do what we do. We find ourselves in a situation where we need to talk about convexity because we actually want to be guided on how we can achieve our optimization goal. Okay, particularly if we're actually uh you know if we are seeking what I call minimization goal. Okay, we need to be able to have a function that can guarantee global minimum. And of course, I remember before now, I've already walked you through, what could qualify a function to be convex. So we're actually going to continue from where we left off on Monday. We are actually going to continue from there today. Okay, so I think I've been able to walk you through different kind of differentiable classes. Okay. In today's lecture, I'm going to continue explaining convexity using different differentiable class, and not only that, I'm also going to, uh, walk you through different kind of convexity. We have a strong converse, we have a strictly converse. So I'm actually going to differentiate between strict converse and strong converse. And of course, I'm going to walk you through other, uh, you know, terminology here. Okay, so I remember we stopped at on this slide on Monday. Now, what is this particular slide talking about? Before coming to this slide, as a recap, we got three differentiable classes that we can actually be used to explain convexity. The first differentiable class that we call C0 is actually you trying to minimize a function that is continuous, but not necessarily differentiable. And I believe I walk you through how we can investigate convexity using that kind of function. Now, another differentiable class is what we call C1. Okay, the C1 actually means you have a continuous function and the first derivative exists. Okay, it can be differentiated up to order one. Now, we also have another class that we call C2. Okay. Uh, another differentiable class that we call C2, where a function is continuous and the derivative actually exists to order two. Now the bottom line is, how can we investigate convexity of such function? Okay, how can we investigate convexity of a function that is continuous and at the same time, the derivative actually exists up to order two? Okay, You can be, you can be able to obtain the first derivative. You can also obtain the second derivative. And that's what I want to show you right now. That's what is going to lead us to the Asian matrix. Now, when you say a delta squared, it means I'm actually performing the second derivative. The f of w is the continuous function that we are actually seeking the minimum value. Now, uh, in a situation where you're dealing with multivariate, where you got a lot of variables, of course, and you want to use a C2 differentiable class, okay, you're actually going to have what I call Asian matrix. This is what you call Asian matrix. If you take a look, give me 1 second. If you, let me see, this is okay. Now, um, if you take a look at the diagonal of this one, the diagonal here is actually, uh, you differentiate with respect to the same variable, twice. That's why you see the W1, the W2, and of course, you also see the W2, the W2, okay, and you also see the W3, the W3, and so on, like that, okay. That's why you're seeing it. That's why it's happening here, okay. Now, in the half diagonal, okay, in the half diagonal, you take a look at this one, you differentiate with respect to W1 the first time, and when you want to differentiate again, okay, you differentiating the resulting expression with respect to another variable. So this is what we call Asian matrix. But you know what? Do you know that I can actually equate mathematically, I can equate that to the transpose of X by X, okay? Particularly in a least square regression, okay, in a least square regression, where we are actually seeking uh, the optimal value of regression parameter. So, we actually do all this. Okay, so I just wanted to take note of this guy now. Okay, so the second derivative of f of w can also be written as S transpose S. We are still discussing second we're still discussing uh the third in the differentiable class, which is what we call the C2. Okay, now what I want us to talk about now, how do we investigate convexity for a particular function that we are trying to minimize, okay, that can be differentiated first and second time. Okay, now, we actually got this matrix, but we're going to impose a condition on the Asian matrix for convexity. And the condition is this. We're going to say, okay, that function under investigation, okay, is convex if and only if, that is greater or equal to 0. We don't want to tolerate any we don't want to tolerate any negativity. We only want to tolerate non-negative values. Now, when we actually have a non-negative values, okay, for all domain, okay, or we're talking about for all domain, for all possible values of W, okay, that we can guarantee a curve upward in every direction. Okay, we can actually because what we are actually targeting, is the global minimum. And for us to be able to achieve global minimum or using the third in the differentiable class, this must hold. Okay, because that is going to make it curve upward. Okay, and when it's curve upward in every direction, that we prevent what I call the algorithm to get stuck. Okay, we don't want our algorithm to get stuck in a local neighborhood. Our intention is, when you get to local neighborhood, is should be able to get out of that. Okay, the only where we want it to stop is the global minimum. And the only condition under which we can actually satisfy that is when we're using the third in the differentiable class that we call C2, we expect this to be non-negative. Okay, now, uh, because of this, there's something that we did in class that we call positive definite, semi-positive definite. Of course, we also play a very huge role here. Okay, now, of course, I remember when you have a matrix, when the matrix A is actually greater or equal to zero, okay, we actually gonna consider a positive semi-definite. When I say that, when I say matrix, maybe I'm actually talking about quadratic form. You remember the last time when I was talking about quadratic form? Okay, well, the quadratic form, okay, has to be, if it is greater than zero, we have a positive definite. If it is greater or equal to zero, we have a positive semi-definite and so on like that, because that's actually a serious implication for eigenvalues and eigenvectors in case we are working with a principal component analysis. When you're working with the principal component analysis, where the matrix factorization is involved, we want to decompose a matrix into simpler pieces that will contain the eigenvalue and the eigenvectors. Okay, so the if we want our eigenvalues to all be non-negative, of course, we expect we actually going to call that positive semi-definite of the matrix is actually required. And that's exactly what I'm trying to say here. Because it is only when you have a greater or equal to zero that the eigenvalues also going to be greater or equal to zero. Don't forget, in principal component analysis, the eigenvalues represent the variances. We don't want variance to be negative. It doesn't make sense if the variance is negative. And because the eigenvalues represent the variance, we actually need to guarantee non-negativity. Okay, so when I talk about quadratic form now, okay, uh, is this guy. Don't forget, I'm still talking about the A matrix here, where all the eigenvalues of that are to be non-negative in a situation, okay, because it is only when the eigenvalues here are non-negative that we actually going to say the quadratic form will also be non-negative. Okay, so I'm going to say this. If we have a matrix A, this is a matrix A. If this matrix is actually having all eigenvalues to be non-negative, automatically the quadratic form of V transpose, okay, A, okay, V also going to be non-negative because the non-negativity is a special requirement here. Okay, in the third differentiable class, if you are trying to figure out if you are trying to investigate the convexity of a function. Okay, now I'm actually going to move right now away from there. Now, please pay attention. Okay, now I want us to do this. Okay, uh, we are in a third differentiable class now. C2. We want to use C2 to investigate convexity, and to be able to do that, let's have an example in statistics. Least square. I know you've already about least square. Which is this guy here? Give me 1 second. Which is this guy? You know what we're trying to do here? XW is actually the model. We are fitting this model to this data set. I need everyone to pay attention now. what are we actually doing here? This is a model and this is data set. We're fitting this model to the data set. Okay. I said from day one when we started this class, I said that we actually want to use model to depict reality. But you know what? The best model cannot give us the best an exact characterization of reality. Okay? I'm going to say that again. The best model cannot give us an exact characterization of reality. If I'm using this model, XW, okay, to model reality, the data set, there's always going to be a gap. And that is why you see a minus. So what this function is trying to do is we want to have a way to minimize the gap between the model and reality. If we go by a way of least square, this is the function that we are seeking minimization. Okay, of. So this is a minimization problem. This is a function now. Now, if I have this as a function now, okay, and this can be differentiated twice, of course. This can be differentiated twice. Any quadratic any function that is quadratic in nature can be differentiated twice. Now, what we're going to investigate when we are investigating convexity is, as I have this f of w, I will differentiate it second time. I will differentiate first time, second time. Okay, and when I do that, it's going to be equal to that. Because if you take a look at this, okay, let me walk you through this the scalar one. Okay. For instance, if you differentiate the first time, if you let me do this. If you do that the first time, okay, if you do that the first time, if I have this one, okay, the first derivative of that W, okay, if you do that the first time, you're doing that with respect to the weight, okay, so two, I'm actually gonna have half, okay, multiplied by 2, okay, then I'm gonna have just this guy here, okay, xw, okay, minus y. That is the first one. Now, when I actually this guy now, I cancel this guy and I cancel that guy. Okay. Now, if you take a look at what I have right now and I try to do the differentiation again, you're going to see that the W is going to disappear. Okay. Okay, because I've gone from a polynomial of degree one to polynomial of degree two to polynomial of degree one, and at the end of the day, I'm actually going to find myself here in a matrix form because the W will be eliminated. Don't forget, I'm actually differentiating with the respect to W, and that's going to lead us to this guy right now. And the moment we find ourselves in this situation, okay, where number one, we need to be, so this guy now is going to be acting as my A. So where do I get which A am I talking about? I'm actually going to go walk you back right now. Give me 1 second. I was talking about the condition here. This is A, right? A greater or equal to 0, and it has to be positive semi-definite, and the combination of A and something is what we call quadratic form, also going to be non-negative. So my A now, okay, is this guy here. Can you see that? That is my A right now. And I said the other time the condition is that A should be greater or equal to 0. Okay. And I also said the other time, okay, on the other page, I said this guy, okay, and A, okay, and that guy, what I mean by the quadratic form, also greater or equal to 0. So because this is my A, I can rewrite the quadratic form to look like this. Can you see that now? Okay, where this guy is actually the A. Okay, we expect that to be greater or equal to 0. But you know what? How are we going to investigate this? I need you to pay attention to this. What I'm explaining now is very, very crucial, and I need you to pay attention. Before moving forward, is there any question? Is there any question before moving forward? I want to know if you are still hearing me clearly. Or can somebody confirm once again if you are still hearing me? Is everyone still hearing me?
Yes, sir.
Okay, thank you so much. Thank you for confirming that. Okay, now the next thing that I wanted to investigate now, what I want to investigate, what our assumption are. Our assumption is that this guy should be the eigenvalue of that guy should be greater or equal to zero. Not only that, the quadratic form of that guy must also be greater or equal to zero. That is what I want to verify now. Because if it is greater or equal to zero, we start celebrating. Okay, we start celebrating that our function here is actually convex, and the moment our function is convex, the optimal value of W that we are looking for is actually going to be unique. Okay, now what I'm going to do right now in investigation, I want to focus this is what I want to verify. Okay, now I want to start verification now. Okay, I want us to get started. Are you ready? Is everyone ready? Is everyone ready for this? Are you all ready? I need somebody to confirm. Are you all ready for this?
Yes, sir.
Thank you so much. Now, I actually want to break things down now, and I need you to pay attention. Okay, now take a look at this guy. Okay, it's also what I have here. Oh, this should be V, not W. That should be V. Okay, you can correct that. Okay, now if you take a look at this guy here, you see what I have here. But do you know mathematically, if I have A, B transpose, we did that the other time. If I have a transpose of the product of A, B, it is the same as B transpose A transpose, according to the mathematical rule of matrices. Now, do you know that if you take a look at this guy, right? Let me do this so that I don't convince you. Like I said, this is X, this is V, right? Now, if you take a look at this guy, I can rewrite it as this because I'm actually using this property. Okay. Now, if I rewrite that as that, okay, now instead of me to have this guy now, this is what I'm actually going to have. Look at that. That's what I'm going to have. Okay, I'm actually going to have XV transpose XV. Now, when I have XV transpose, oh my God, what is going to happen now? Okay, so we find ourselves right there now. Give me 1 second. Okay, now we now find ourselves. Okay, let me do this. Now, this is where we are now. Okay, do you know I can just let this guy, I can say, okay, let another variable be equal to xv, right? If another variable equal to that, then I can simply write the all of these as u transpose u. Okay, and if u equal to xv, so u transpose also going to be equal xv transpose. Take a look at that. Is that not beautiful? Okay, so if I not get here now, if I get here now, okay, I now have a U transpose U. Do you know that U transpose U geometrically, okay, if I do U transpose U is the same thing as a square norm. Please pay attention. That's a square norm. Okay? U transpose U is a square norm. Now, if this guy is a square norm, then it means this guy is also going to be that. And we have verified. Take a look at this. I told you in class the other time, any norm is convex. The square of norm is convex. Now we're able to verify that, okay, this guy is actually equal to that. Now, if that's equal to that, now, Okay, so what I mean is that this if a norm is a convex is convex, the square of a norm is convex, then the square of that is guaranteed to be greater or equal to zero. And you know what? If that happens, then I'm actually going to say, okay, solving the first derivative, the W, the value that we're actually going to get at the end of the day is going to be global minimum. Is there any question on this page before I move to the next page? Is there any question on this page before I move to the next page? Okay, silence implies that you understand that. Okay, now I'm going to move to the next page now. Okay, so moving to the next page now. Okay, now showing that the function is a converse. I think I've walked you through that. Okay, let me tell you this. We have some common approaches to show that a function is converse. You remember in the last class, okay, the class that we have on Monday, I said that they are kind of algebraic operations that can preserve convexity. Number one, you remember non-negative scaling. When I multiply a converse function by a positive number, okay, it's still going to preserve convexity. If I sum if I add two functions that are converse, the resulting function is still going to be converse. When I do the mass of a particular function that is converse, it's still going to be converse. When I do the composition of a function with linear, it's still going to be converse. But let me tell you this, it is not all composition of function that is converse, but if you are doing the composition with linear, it's actually going to be converse. I think I walk you through this on Monday. Now, and today, I just walk you through using the third in the differentiable class. Okay, the moment we're able to establish that when the Asian matrix is greater or equal to zero, we can also say we can achieve convexity in that direction. Okay, and I remember Monday, I actually talked about, I gave you an equation that you can, that represent convexity. Okay, so that very, give me 1 second. So that very equation is what you're actually seeing now. Take a look at this one. When I said when you draw any two points in a set, you draw 2 points from a set and you draw it or which represent a chord, we expect we expect we expect that to stay inside the set, okay? And we said the function should be less or equal to. So this is the chord right now. Okay, what you're seeing here is a chord, and of course that guy is actually the function that contain any 2 points, okay, between W and V. Okay, so that's what you have. Okay, 1 second. I think I now I'm actually uh going to say this that uh, we deal with a lot of minimization problem in statistical machine learning, particularly when you talk about logistic regression, you talk about support vector machine and so on like that, where we want to minimize what you need to do. If you want to use the idea of third differentiable class that we call C2, all what you need to do is to rewrite the function in Asian matrix notation. And if you can verify the positive semi-definiteness, you should be fine. You should be able to verify convexity. I want to walk you through right now. Okay, the role the positive semi-definite and the positive definite actually play, and not only that, the generalized inequality. Okay, remember I said this the other time. Okay, when we have a matrix, and of course, the it is greater or equal to zero, or the eigenvalues of that is greater or equal to zero. You have a positive semi-definite. If it is strictly greater than zero, it is going to be positive. Take a look at that. The difference. This is positive definite, but when it includes zero, it is positive semi-definite. The semi is the fact that it can be equal to zero. That is what I mean. And whatever that affects, the nature of this is also going to affect their corresponding quadratic form. Okay, you can see that. Here, when this guy can be greater or equal to zero, the quadratic form can also be greater or equal to zero. When this guy is strictly greater than zero, the quadratic form also going to be greater than zero. So in a situation, okay, in a situation where the quadratic form is actually strictly greater than zero, then it means all eigenvalues should be greater than zero. And not only that, the quadratic form should be straighter than greater than zero. And let me now tell you the implication. This is actually more stronger than this one, because the implication, when a situation where we have a positive definite, you know what happened? Then the determinant of A will not be singular. And when the determinant of A is not singular, of course, it means you can find the inverse of A. That is the bonus here. And if I'm able to find the inverse of a matrix, particularly in a linear regression setup, okay, if you can find the inverse, then you will be able to estimate the regression parameters. Okay, so that's what I mean. Now, another thing I'm going to talk about is this. When you have two matrices, you have A greater than B. The moment you look at the difference between the two matrices, if it is positive semi-definite, okay, then we're actually going to have a two quadratic form, the quadratic form involving A and the quadratic form involving B. You can compare them, okay? So if you take a look at what I have right now, this is a quadratic form involving A. This is a quadratic form involving B. So if A is greater or equal to B, okay, in such a way that A minus B is positive semi-definite, then the quadratic implication is that the quadratic form that has to do with each of that will be one, the one that has to do with A will be greater or equal to the one that has to do with B. I want to take you to an example now. I need you to pay attention now. Okay, I'm going to walk us through an example now. Okay, before going into an example, we've been talking about convexity. The question now, we have convexity in general. We have strict convexity. We have strong convexity. Okay, at times, we may need strong convexity. Okay, it is called strong because that convexity, the degree of convexity in strong is actually higher compared to this to the straight one. But you know what I want to do right now? I need you to pay attention. I actually want to use the third in the differentiable class to distinguish between the type of convexity. And I want you to pay attention now. We are using the third in the differentiable class. Don't forget, the first in the differentiable class is when you have a function that is continuous but not differentiable, not necessarily differentiable. The second in the differentiable class, when you have a function that is continuous and the derivative exists up to order one, and the third in the differentiable class is what we call C2, where the function is continuous and it is differentiable up to order two. Okay, now you know what I want to do now. Within this differentiable class, can we differentiate between different type of convexity? Okay, so using the different type of convexity, the moment I have this guy, I'm actually going to say, okay, it is convex. If I want to know what is the degree of convexity, okay, if it is greater, strictly greater than zero, I'm actually going to call that straight convex. Okay, that's what we call strictly convex. But what if in a situation where it is actually greater or equal to mu I, where mu is greater than zero, where I is identity matrix, then we're going to call that strongly convex. Now, let me tell you this. At times, when we're seeking minimization problem, we know we normally require strong convexity. Because let me tell you this, if the function has a strong convexity, that particular if we are using a gradient approach, of course, we are using a gradient approach here because this actually involve derivative of that we affect the speed of the gradient descent. Strong convexity affects the speed at which the gradient descent is traveling is going to do that in a way that is not going to get stuck in a local minimum. Don't forget, what we need is a global minimum, okay? To be able to guarantee global minimum depending on the function that we have, okay, at times strong convexity may be required. Okay, now I'm actually moving now. I'm moving. Okay, we want to walk you through example. But you know what? If I'm actually working on a univariate on a univariate situation where maybe I'm actually seeking to minimize f of w. Okay, if I'm seeking to minimize f of w, okay, I only have one variable at a time, and I want to use the third in the differentiable class, which we call C2, to investigate different type of convexity. It is actually convex if I do the second derivative and this is greater or equal to zero. It is strictly convex when it is greater than zero, and when it is equal to mu, where mu greater than zero, it is or strongly convex. And I'm going to walk you through an example now. Now, let me tell you this. Take a look at this guy. If my f of w is w, if I differentiate the first time, don't forget f of w we mean the the w, the f. It's like I mean maybe the f dw, right? The f dw is actually 1. Okay. Now when you differentiate the second time, because that one is a constant, right? Okay, that would be 0 everywhere. The fact that I have equal to 0, that is just converse. That is just converse. Okay? That is just converse. But if you take a look at another function here that we call exponential raised to power w, when you differentiate first time, it's still going to be exponential raised to w. When you differentiate second time, it's still going to be exponential raised to power w. Now, if you now want to see, if you want to look at the type of convexity, that now depend on the domain of the w. Okay, for all positive W, this guy is going to be greater than 0. For all positive W, okay, that guy is going to be greater than 0. So, but for negative, it's not going to be greater than 0. If I for negative, it may not even be convex, okay, because it's going to be less than 0. That's against convexity, okay. Now, if you take a look at another function now, okay, which is this guy, okay. because of the fact that this is quadratic in nature. If you do the first derivative of this guy, it's actually going to be W. If you do the second derivative and you get a particular number, okay, one, that one is the mu that we talk about here, okay? That was why I said mu equal to one, and one is greater than zero, okay? Now, that is what we call strongly converse, okay? In the next assignment, I'm actually going to give you uh, different kind of functions. I can ask you to use either the first in the differentiable class or the second in the differentiable class or the third in the differentiable class to investigate for convexity. I can actually do that. Okay? Now, is there any question for me before moving to the next slide? Is there any question for me before moving to the next slide? Can somebody confirm again if you are still hearing me clearly? Is everyone still hearing me?
Yeah, we can hear you well.
Okay, thank you so much. Thank you so much. Now, I'm actually moving now to the second one, to the next slide. I'm going to spend my time on this slide because, in fact, let me see. Give me 1 second. I'm going to see. Okay. Okay. So, okay. That will be for the Friday because we are still using this material for Friday as well. Wherever we stop here today is where we're going to continue on Friday. Now, I want to talk about this. I want to investigate using regularized least squared. The other time I said, we said this guy equal to this guy, right? But you know what? In the ridge regression, okay, there's a regression that we call ridge, where in order for us to control over parameterization in a model, in order for us to reduce noise, in order for us to solve a problem of overfitness, because we don't want a situation where our model will capture noise. We don't want a situation where our model is going to perform greatly on training data and is going to perform poorly on unseen data. Because of that, we normally introduce regularization parameter. We do that in bridge regression. We introduce a lambda high. Okay, but let me tell you this. If I introduce a lambda high, the same way that I investigated this guy the other time for positive definiteness, I'm now going to investigate the whole thing. But let me tell you this. Don't forget, because I'm adding, okay, don't forget addition of two converse function can see preserve convexity. Now, if I want to investigate that, okay, take a look at this guy. Okay, uh, the quadratic form of it is this guy. This is a quadratic form. You remember the other time when I'm talking about if I have a matrix A, if I want to get a quadratic form, I'm actually going to use transpose of V multiplied by that A, V. So this is our A here now. We got a new A. Okay, now we want to investigate what we investigated the other time. Let's take a look at the way it's going to be done. So, which is this guy now? We're here now. Okay, so what I need you to do now, we're actually going to pre-multiply and post-multiply. Take a look at that. This is going to multiply this and multiply this. Can we write the result out? I'm actually going to have the transpose of that. I'm actually going to have S transpose S. Okay, and I'm going to, because I'm multiplying this by this one, I'm actually going to have V, then plus, okay, it is now the turn of this guy. Now I want to use this guy to multiply this to also multiply this. So which is going to be V transpose or lambda I, and V. Okay, now when you take a look at this guy, don't forget this guy we verified the other time. This particular guy here, if I actually want to simplify that, I can write XU, okay, transpose, okay, which is going to be for the first two. Then I'm going to write X or XV, okay, sorry, this is V. Now, when you take a look at this one is a square norm, okay? That's a square norm of XV, okay? That's a square norm of SV. Now, when you take a look at this, my lambda I is just lambda because I is an identity. Okay, if I have this guy now, okay, and I have this guy, okay, lambda is a constant. If I bring a lambda out, I'm actually going to have the V transpose V. Oh my God, this guy is also a square norm. So that's why you see lambda here, and you have this guy, which is a square norm, which is the same thing as that. And you know what? When you have stuff like this right now, okay, of course, the square norm. A norm is convex, a square norm is convex, and the fact that we have a square is going to be greater than zero. That's why you actually see, okay, this guy is greater than zero, this also greater than zero. Okay, provided the lambda is positive, we have to impose that condition. It's positive, so it's greater than zero, and v is not equal to zero. So this is greater than zero, got greater than zero. If I add them up, I'm also going to have greater than zero. Now, do you know the breakthrough that we have in a rich regression today is because of the fact that we are able to establish the positive definiteness of the quadratic form involving this function. And what is the consequence of that? The consequence of that is that this guy is going to be invertible. Because if it is not invertible, we're not going to have a solution to the problem. So with the invertibility now, the solution is actually going to be unique. The stationary point is actually going to make sense. Okay? And that's exactly what we mean. Okay. Now, uh, you know what I'm actually gonna do? I'm actually gonna start from strong convexity on Friday. And you know what I'm gonna do? You know what I've done today? Part of what I've done today, I've actually investigated types of convexity within the third differentiable class. But you know what I'm going to do on Friday? What I'm going to do on Friday, can we also have a way to investigate the type of convexity using the first differentiable class that we call C0, okay, that we call C0, and the second differentiable class that we call C1. Okay, so we're actually gonna start from here on Friday. Is there any question for me today before I go? Is there any question for me today before I go?
Yeah, I have one question.
Okay, go ahead.
I had a question about the team formation for the project that we'll have later in the semester. And I was
Okay.
wondering when that could happen or when we could expect that to happen.
Okay, actually, it is very, very early in the semester to talk about project because we're still going to do a lot of topics because if I actually start the project right now, uh, because there's still going to be some topics that may interest you. So I'm actually going to say when we get to the midway in the semester, possibly let me just say ending of February or the beginning or the early March, then I'm actually gonna give information about how the project is gonna go.
Oh yeah, yeah. I was just curious. That's why. Thank you so much.
You're welcome.
Thank you.
Okay, is there any question at this time? Is there any question? Is there any question? Okay, in the absence of question, I want to appreciate every one of you for attending my lecture today on Zoom. Of course, on Friday, we actually are going to return to in person. Before Friday, make sure you all stay safe. Bye for now, everyone.
Thank you.
Thank you.
You welcome. Thank you too.